Pick up a soda can. Right now, if there's one near you, feel the weight of it, or really, the lack of weight. That hollow, almost nothing feeling in your hand. Now consider this. The atoms inside that can are older than the Earth itself. They were forged inside a dying star that exploded billions of years before our Sun even existed. That star burned out, scattered its guts across the galaxy, and some of those atoms drifted into the cloud of gas and dust that eventually became our solar system, our planet, the ground under your feet, and yes, that flimsy little can you're holding right now. And here is the part that genuinely keeps me up at night. That exact same material, those same atoms in that same metal, was once so rare, so impossibly precious, that governments posted armed guards around small pieces of it. Not because they were afraid someone would steal state secrets, because the metal itself was worth more than most people earned in a year. I'm not talking about gold. I'm not talking about platinum. I'm talking about aluminium. The same stuff your kitchen foil is made of, the same stuff you crumple up and toss in the recycling bin without a second thought. 60 years ago, throwing away an aluminium object would have felt like burning a stack of cash. 150 years ago, owning a small piece of it meant you were either a scientist or royalty, and honestly, the line between those two things was thinner than you'd expect. The story of aluminium is one of those stories that sounds completely made up right up until you check the facts, and then it becomes even more unbelievable. It's a story about a material that was everywhere and nowhere at the same time. About a lock that took humanity over a century to open. About two young men who cracked that lock simultaneously from opposite sides of the world without ever knowing each other existed. About how one discovery collapsed the price of the most coveted substance on the planet by hundreds of times in just a few years. And about how that same material went on to change warfare, reshape cities, make flight possible, and quietly end up in every single home on Earth. I want you to really sit with that recycling bin image for a second, because it's going to anchor everything that comes next. You walk past that bin every day. You drop cans in it without looking. Maybe you squash them flat with your shoe first. And what you're actually doing in that moment, without realizing it, is completing a cycle that involves stellar explosions, billions of years of geological patience, the obsessive work of dozens of chemists who died frustrated, two young men in two cramped workshops on two different continents, and enough electricity to power a city of over 1 million people. That crushed can in your hand is the end of one of the strangest journeys any material has ever taken. And most people don't know a single chapter of it. I've been sitting with this story for a long time now, and every time I think I've found the most surprising part of it, I turn another corner and find something even harder to believe. So I want to share it properly. Not the textbook version, not the dry chemistry lesson. The actual story, with all the strange details that usually get left out. We're going to move around in time a little, because that's honestly the only way to do this story justice. We'll start in the middle, where the world breaks open. Then we'll go back to the beginning, to the stars, to the clay, to the locked doors. And then forward again, through wars and workshops and kitchens and rocket engines, all the way back to that can in your hand. If this kind of story is what you're here for, do me a favor right now and subscribe, and hit the like button if you're feeling it. It genuinely makes a difference and helps this reach people who'd love it too. So, Let's start with the day everything changed. Somewhere in a mid-sized industrial city, not a capital, not a famous place, just a working city full of factories and coal smoke and the sound of metal on metal, a small company made an announcement that sent a very specific group of people into something close to panic. The announcement was quiet by today's standards. No press conference, no viral post. Just a production figure and a price. But the people who understood what that number meant felt it in their stomachs immediately. The price of aluminium had just collapsed. Not dropped, not corrected. Collapsed. In the space of a few years, a material that had been trading at prices comparable to precious metals had become cheap enough to sell by the bucketful. Investors who had staked serious money on the metal's scarcity were staring at losses that made no sense. Craftsmen who had built careers working with it as a luxury material suddenly found their entire professional identity evaporating. And a handful of aristocrats who had collected aluminium objects the way other people collected diamonds were sitting in their drawing rooms trying to understand how their treasures had turned into scrap overnight. The cause of all this chaos was not a war. It was not a newly discovered deposit somewhere. It was not political. It was a process, a method. A way of doing something that two complete unknowns had figured out almost simultaneously, without coordinating, without communicating, without even knowing the other one existed. One was working in a converted outbuilding behind his family's house. The other had a cramped workshop in a city apartment block. Neither of them was famous. Neither of them was wealthy. Both of them were in their early 20s. And between them, without planning it, they had just broken the world's most exclusive material club wide open. The question is, how they did it. And to answer that, we have to go back much further than either of them. We have to go back to a time before the Earth existed at all. The most common metal on Earth was the last one humanity ever discovered. Let that sink in for a second. Not the rarest, not the most exotic, the most common. The one that makes up nearly 1 in every 12 atoms in the Earth's crust. The one sitting in every handful of dirt, every lump of clay, every grey chunk of rock you've ever kicked off a path without thinking twice. Geologists will tell you that if you took all the metal in the top layer of the Earth's surface and sorted it into piles, the aluminium pile would dwarf everything else combined. Iron, copper, zinc, lead, all of it, smaller piles. Aluminium wins by a margin that isn't even close. And yet, the first person to hold a piece of actual aluminum metal in their hand did so less than 2 centuries ago. Think about the timeline for a moment. Humans were smelting copper thousands of years ago. Iron has been worked for over 3,000 years. Gold has been worn as jewelry for 7,000 years. These metals were found, understood, and built into entire civilizations, while aluminum sat in the clay beneath everyone's feet, completely untouched, completely invisible, the most abundant thing on the planet, and simultaneously, the most inaccessible. I keep coming back to this image when I think about it. Imagine a library where the most important book in the building is sitting right on the front desk, in plain sight, cover facing up. Not locked in a vault, not hidden in a back room, right there. But every single person who walks in looks straight past it because the cover looks exactly like a piece of wood. That's aluminium. It was never hidden underground. It was never scarce. It was in the clay on the riverbank and the grey rock on the hillside, and the soil under the wheat fields. It was everywhere, all the time, for billions of years. And nobody could get to it. Not because they didn't know it was there, eventually they figured out it had to be there, but because getting to it required a tool that simply had not been invented yet. Here's the strange part of the strange part. By the early 19th century, chemists already knew aluminum existed. Not suspected, knew. They could measure its effects in compounds. They could calculate its properties. They could name it, describe it, theoretically, predict how it would behave. They just couldn't make it appear. It was like knowing with complete certainty that there's a room behind the wall, being able to describe exactly what's inside, and having absolutely no way to open the door. The frustration in the scientific literature from that period is almost palpable even now. You can feel it in the careful, restrained language of men who are deeply, quietly furious at a problem they cannot solve. So what was the door? And why was it so hard to open? That's where part 4 of this story begins. And honestly, once you understand the chemistry, even just the basic shape of it, the 200-year delay stops feeling like a failure of human intelligence and starts feeling almost inevitable. Friends, if you're enjoying this story so far, please subscribe and leave a like. It genuinely helps more than you might think, and there is a lot more to come. Here is the problem with aluminium in one sentence. It loves oxygen more than any other common metal on Earth, and it will not let go under any circumstances that humans could create before the age of electricity. I want you to picture what happens when you leave an iron nail outside in the rain. Over days and weeks, it turns red and flaky. That redness is iron oxide, rust. Iron that has grabbed onto oxygen from the water and the air. The bond between iron and oxygen is real, but it's beatable. You can heat iron ore in a furnace with charcoal, and the carbon in the charcoal will physically pull the oxygen away from the iron, freeing the metal underneath. That's been the basic logic of iron making for thousands of years. The carbon wins the tug of war. Simple, effective, scalable. Now try the same thing with aluminium. You take aluminium oxide, which is what you find in clay and rock, and you put it in the hottest furnace you can build, and you add all the carbon you want. Nothing happens. The aluminium holds onto its oxygen like it's the last thing it will ever have. The bond is so strong, so deeply stable at the atomic level that carbon simply cannot outcompete it. The chemistry doesn't favor it. At any temperature, a real-world furnace can sustain. Aluminum oxide is more stable than carbon dioxide, which means the carbon has no incentive to grab the oxygen away. The reaction just doesn't run in the direction you need. This is not a small engineering problem. This is a thermodynamic wall. And for most of human history, nobody had a tool powerful enough to climb it. The furnace was the only tool anyone knew. Bigger furnace, hotter fire, more carbon. None of it worked. The aluminum sat in its oxide like something sealed in concrete, stable, patient, completely indifferent to every chisel humanity tried to swing at it. What makes this genuinely haunting is that the solution, when it finally came, used a force that didn't exist as a practical technology until the 19th century. Electricity. Specifically, the ability to pass a powerful electrical current through a liquid containing aluminium compounds and force the aluminium atoms to move, to separate, to collect at one end of the circuit as pure metal. Not persuade them chemically, Force them physically, using raw electrical energy to break a bond that no chemical process could touch. But here's the thing about that solution. It sounds simple when you say it like that. Pass electricity through the right liquid and collect the metal. Straightforward. Except that the right liquid turned out to be one of the hardest parts of the whole puzzle. Because aluminium oxide melts at a temperature so extreme, it makes steel production look gentle by comparison. And you can't run electrolysis on a solid. You need a liquid. So you either melt the aluminium oxide directly, which requires temperatures that were simply impossible to maintain in any practical setting at the time, or you find something else, some other substance that aluminium oxide will dissolve into at a much lower temperature, and you run the electrolysis through that instead. Finding that substance took decades. And the two people who eventually found it, working in their separate workshops on separate continents, were closing in on a solution that dozens of brilliant scientists before them had spent their careers trying to reach. The door was almost open. But first, we need to understand exactly how long people had been hammering on it, and just how close some of them came before falling short. The aluminium in your kitchen was cooked inside a star that no longer exists. I don't mean that as a metaphor, I mean it literally, physically, as a statement of documented fact. Every atom of aluminium on this planet was synthesized through nuclear fusion reactions inside massive stars that burned out and exploded billions of years before our sun ignited. The temperatures inside those stars reached hundreds of millions of degrees. The pressures were so extreme that lighter elements were forced together to form heavier ones, and aluminium was among them. When those stars died, they didn't just go dark. They detonated outward, scattering everything they had ever made across enormous regions of space. That scattered material drifted and cooled, and eventually, over millions of years, was pulled together by gravity into new clouds, new disks, new solar systems. Ours was one of them. And the aluminium those ancient stars had forged came with it, settling into the rock and clay of a young planet that had no life, no oceans yet, no atmosphere worth speaking of. This is not a poetic embellishment. This is the actual chain of events that put aluminum in the ground beneath your feet. The element predates Earth by a significant margin. It was old before our planet existed, and when the solar system was still forming, when the rocky inner planets were still being assembled from colliding debris, aluminum was already there in the mix, bonding eagerly with oxygen and silicon and calcium, locking itself into the first minerals that would eventually become the crust of the Earth. There is a way to see this with your own eyes, no telescope required, no special equipment. On a clear night, look at the moon. The surface is divided into two visually distinct regions. The dark patches are ancient lava plains, relatively smooth and flat. The bright regions, the pale highlands that catch the light and hold it, are something else entirely. Those are mountains and upland plains made primarily from a rock called anorthosite, and anorthosite is rich in calcium feldspar, which is an aluminum-bearing mineral. The brightness you see is partly a reflection from aluminum-containing rock. The moon is not just a grey, dead ball. Parts of it are literally shining with aluminum compounds, visible to the naked eye from 240,000 miles away. Earth is built the same way. The difference is that here, billions of years of geological activity, erosion, water, life, have mixed and sorted and layered things to the point where the aluminum-rich minerals are spread through almost everything. the clay on a riverbank, the feldspars in a granite cliff, the red laterite soil in tropical regions, the grey powder a stonemason breathes in when he cuts certain types of rock. It is everywhere, woven into the fabric of the planet in a way that nothing else quite matches. And for most of human history, it was completely inert to human hands. Present, abundant, utterly unreachable. What I find almost unbearable about this, in the best possible way, is the patience of it. This material travelled billions of light-years worth of stellar history to end up in the ground. It sat in the crust of the Earth through the entire span of human civilization, through the invention of writing, through the building of every ancient monument, through every empire that rose and fell. It was in the soil the farmers ploughed, and the clay the potters shaped, and the rock the miners dug. And not one person in all of that time ever held a piece of the pure metal in their hands. The chemistry wouldn't allow it. The knowledge wasn't there. The tool, meaning electricity used in a very specific way, didn't exist yet. So the aluminium waited. Quietly, with no urgency, as things that are 4.5 billion years old tend to do. But here is what makes the waiting even stranger. While the pure metal was completely inaccessible, its compounds were not. And people had been using those compounds in ways that shaped entire industries and cultures for thousands of years, without ever once asking what was actually inside them. Ancient dye workers in warm, dry regions near large inland seas discovered that certain white crystalline salts collected from mineral deposits and dissolved in water had a remarkable property. If you soaked raw fabric in that solution before applying plant-based dye, the color bonded deeply into the fiber and held fast through washing, through sun, through years of wear. Without the treatment, the color faded within weeks. With it, the color stayed vivid for the life of the garment. These salts were traded across hundreds of miles of coastline and desert. They were stored in merchant warehouses alongside spices and metals. They were listed in trade records as a strategic commodity, something worth controlling access to, something worth paying serious money for. Those salts were aluminium compounds, specifically a form of aluminium sulfate combined with potassium. The aluminium ions in solution were doing the chemical work of gripping the dye molecules and anchoring them to the fabric fibers. The craftspeople who used this process had no concept of aluminium as an element. They had no framework for asking what was inside the salt at the atomic level. They knew what the salt did. They knew how to use it. That was enough. The idea of breaking a useful substance down into its components and asking what each component actually was, that kind of question simply wasn't part of how people thought about the material world for most of human history. The same compounds showed up in wound care, in leather production, in food preservation, in water treatment. Across multiple ancient cultures, spread across thousands of years, people were repeatedly discovering that this particular class of white mineral salts was useful in a striking variety of situations. The aluminium was there every single time, doing the work, invisible as an element, unrecognized, unnamed. It took a specific kind of mind to finally stop and ask the deeper question. Not what does this substance do, but what is this substance made of? And when that question finally got asked seriously, the answer that came back was both fascinating and maddening. There's something inside these compounds, something metallic, something new, and we have absolutely no idea how to get it out. 5 of the greatest scientific minds of the 19th century dedicated significant portions of their careers to finding aluminium, and every single one of them failed. Not because they were careless, not because they lacked intelligence, because the problem was genuinely, structurally harder than anything chemistry had faced before. And the way each of them failed is almost as interesting as the final solution, because each failure was actually a step, a piece passed forward, a door partially opened by someone who couldn't quite get through it themselves. Let me walk you through this the way I think about it, not as a list of names and dates, but as a relay race where nobody could see the finish line and nobody knew they were passing a baton. The first serious runner was a man working in a northern European university town, surrounded by the smell of sulfur and heated glass and the particular dry dustiness of a chemistry lab in the early 1800s. He had already made a name for himself studying mineral compounds, and he turned his attention to the white powder that kept showing up when aluminum-bearing minerals were broken down chemically. He heated it, dissolved it, reacted it with various substances. He confirmed that something metallic was definitely inside it. He wrote up his findings carefully and passed the problems of the next generation. He never got the metal out, but he gave the next person a cleaner map of the territory. The next runner picked up that map and added electricity to the equation. This was a researcher who had already used electrical current to pull other metals out of their compounds, and he was confident the same approach would work here. He built his apparatus, connected his batteries, ran current through dissolved aluminium compounds, and watched. Something happened at the electrode. Something with a slight metallic look. But it was contaminated, mixed with other elements, not pure, not definitive. He published cautiously. He proposed a name for the theoretical metal. He got close enough to smell it, figuratively speaking, but not close enough to hold it. The problem passed on again. Then came a man working in a city apartment with a table covered in glass vessels and copper wire, doing chemistry the way people did it then, by hand, by smell, by color change, by the sound of a reaction fizzing or going quiet. He tried a completely different approach, abandoning electricity and going back to pure chemistry, using highly reactive metallic substances to try to physically displace the aluminium from its compounds. He produced something. A residue with a slight sheen, a hint of metallic character. He announced it cautiously. The scientific community received it with cautious interest, and then a younger colleague examined the result more carefully and concluded it was not quite pure enough to count as a definitive isolation. Back to the drawing board. Again. What strikes me about this sequence, when I sit with it, is not the failure. It's the stubbornness. Each of these men knew the problem was hard. Each of them had read the work of the people before them and understood exactly where the difficulty lay. And each of them sat down anyway, in their cold labs and cluttered workshops, and tried again. That quality, the refusal to accept that something is permanently impossible just because it has been impossible so far, is the thing that actually moves science forward. Not genius alone. Stubbornness plus method, plus the willingness to hand the problem to someone else when you've reached your limit. One researcher in particular spent the better part of 2 decades returning to this problem between other projects, refining his methods, trying new approaches, getting incrementally closer. The image I have of him is not the triumphant scientist of popular imagination. It's a man in his 50s, still at the same bench he was at in his 30s, still working on the same problem, still not satisfied with what he has. That kind of commitment is either inspiration or obsession, and honestly, it might be both. But here is what all of these near misses had in common, and this is the thing that explains why the breakthrough, when it finally came so fast and felt so sudden. Every one of these researchers was working around the edges of the real solution without quite seeing it. They were all trying to find a way to either chemically extract the aluminium or electrically extract it from its pure oxide. And both approaches kept hitting the same wall. The chemical methods weren't strong enough. The electrical methods needed a liquid, and the oxide wouldn't melt at any practical temperature. The solution required someone to stop trying to attack the problem directly and instead ask a different question entirely. Not, how do we break down aluminium oxide, but what else can we put it in? What other liquid can we dissolve it into so that the electrolysis can actually run at a temperature we can manage? That shift in the question was everything. And the two people who made that shift did it independently at roughly the same time without knowing each other existed. One of them had a very specific personal reason to care about solving this. He had sat in a classroom and been told, directly and plainly, that whoever cracked this problem would change the world. He took that personally. And when he left that classroom, he went straight to work. There was a man who worked alone in a small outbuilding at the edge of his family's property. The space was barely large enough for a workbench and a few shelves. In winter it was cold enough that he could see his breath. The floor was packed dirt. The lighting was poor. And in that space, over months of methodical work, he ran through dozens of different mineral compounds, testing each one as a possible solvent for aluminum oxide at manageable temperatures. Most of them failed immediately. A few showed partial promise and then fell apart on closer inspection. He kept notes in a journal that still exists, and reading the entries is like watching someone walk down a very long corridor, opening door after door, finding nothing, not stopping. Then he found the mineral. A pale, slightly translucent substance with a faint blue-grey tint found in certain volcanic and sedimentary deposits, composed of sodium, aluminium, and fluorine in a specific arrangement. When he melted it and added aluminium oxide to the liquid, the oxide dissolved cleanly at a temperature his setup could sustain. He ran current through the mixture. Aluminium ions moved. They collected at the electrode. They became metal. The first pieces that formed were small, barely worth describing physically. A few bright specks on the surface of a graphite rod catching the lamplight. But they were real. They were pure. They were aluminium, pulled from its compound by electricity in a workshop with a dirt floor by a man in his early 20s who had been told this was possible and simply believed it. He didn't pause to celebrate. He scooped up what he had, wrapped it in a cloth, and went to find the professor who had told him the world was waiting. Before that young man with dirt on his hands and aluminium specks on his graphite rod ever stepped into a workshop, a head of state had already decided this metal belonged to him personally. Not to science, not to industry, to power. And that decision, made in a palace dining room with candlelight flickering off polished silverware, set the stage for one of the most bizarre status symbols in the history of human civilization. Let me take you back a little, because this part of the story runs parallel to the laboratory failures we just walked through. While chemists across Europe were grinding away at the problem in their cold rooms and cluttered benches, word had quietly reached the highest levels of government that something extraordinary might be coming. A metal lighter than anything known, strong enough to be useful, resistant to rust and rot. The kind of material that made military planners lean forward in their chairs. Lighter armor, lighter weapons, lighter equipment for soldiers who marched for days carrying everything they owned on their backs. The strategic implications were obvious to anyone who thought about them for more than 30 seconds. So a powerful ruler, the kind of man who had entire ministries devoted to thinking about what the next war might require, summoned a chemist to his official residence. Not a polite letter of inquiry, a summons. The chemist arrived, explained what he knew about the metal and what he believed was possible, and left with a commitment of royal funding and a very clear sense of what was expected in return. Results. Fast ones. The chemist, a driven and ambitious man with a talent for self-promotion that matched his talent for chemistry, went to work with resources he had never had before. A proper facility, assistants, equipment. And within a few years, he had something that none of his predecessors had managed. Not a grey powder, not a few specks on an electrode. Actual ingots. Pourable, castable, holdable pieces of aluminium metal, produced in quantities that could be measured in meaningful units rather than fractions of a gram. The ruler was shown the ingots and immediately began thinking about how to display them. This is the part that reveals something important about how status works. The metal was expensive because it was hard to make. Since it was expensive, owning it signaled wealth and power. And since it signaled wealth and power, the ruler wanted it in the most visible possible place, at the most visible possible moment. He chose the dinner table. Picture a formal state banquet. Long tables covered in white cloth. Crystal catching the light from chandeliers overhead. Dozens of guests in formal dress, the kind of clothing that takes an hour to put on correctly, seated in strict order of rank and importance. The food arrives on silver platters served with silver utensils because silver is what wealthy people eat with. That is the understood social language of the table. Silver equals status. Silver equals wealth. Silver is the best you can offer a guest. Except at this particular table, the host is eating with something different. His fork, his knife, his spoon are not silver. They are lighter. They have a softer sheen, cooler to the touch, with a surface that catches light slightly differently than any metal the guests have seen before. And the guests are eating with silver. Not because the host is being stingy, because silver is the lesser material, because the thing the host is holding is so new, so rare, so expensive to produce, that silver doesn't even compete. The guests are getting the downgrade. This actually happened. It was witnessed by people who wrote it down, and when I try to imagine being one of those dinner guests, picking up a silver fork and watching the host handle something you've never seen before, something that costs more than most people earn in years, I understand exactly why the story spread so fast and so far. It was a masterclass in making a material feel important through pure social theatre. The metal began appearing in small luxury objects, decorative pieces, scientific instruments, gifts exchanged between governments as tokens of prestige. Collectors acquired tiny samples the way people acquire rare art. The price remained extraordinary. The supply remained tiny. And that combination, genuine scarcity plus genuine usefulness, plus the endorsement of the most powerful people in the world, created the perfect conditions for a myth to form around the metal. The myth that this was the material of the future, that whoever controlled it controlled something fundamental. And then a specific decision was made that pushed the myth to its absolute peak. A national monument, a towering stone structure that had been under construction for decades and was finally nearing completion, needed a capstone, the top piece, the element that would sit at the very highest point of the tallest structure in the country. The architects and engineers considered their options. They needed something that would not corrode, something that would conduct electricity safely during storms, something that communicated the ambition and achievement of the nation that built this thing. They chose aluminium. A craftsman was commissioned to cast the piece. It was not large. It would sit in your two hands comfortably. But it weighed more in terms of pure material cost than almost any comparably sized object that had ever been made for a public building. Before it was installed, it was put on display. People came to look at it the way you look at something in a museum case, leaning in close, not quite touching the glass, aware that they are in the presence of something genuinely rare. Many of them had never seen aluminium before that day. They would tell their children about it. The piece was installed at the top of the structure on a cold December day, secured in place by workers who probably had no idea they were handling an object worth more than they would earn in several years of labor. It caught the pale winter light and held it. The crowd below craned their necks upward. And at that moment, aluminium reached the absolute pinnacle of its prestige. The highest point of the tallest structure in the country, chosen above gold, above bronze, above every other option available. It was also, though nobody knew it yet, almost exactly the moment everything was about to change. Because on that same cold December day, somewhere far away, a young man in a dirt floor workshop was running electricity through a pale, melted mineral and watching bright specks form on a graphite rod. The peak and the collapse were happening at almost the same time. The world just hadn't caught up yet. Two young men who never met, never wrote to each other, never even knew the other existed, solved the exact same problem using the exact same method in the exact same year. The odds of that happening are so low that when you first hear it, it sounds like the kind of detail a novelist invents to make a story feel more dramatic. But it happened. And the way it happened tells you something important about how breakthroughs actually work, something that the lone genius version of history always gets wrong. We left one of them in his dirt floor workshop, holding a cloth with aluminum specks on it, heading to find his professor. Let's stay with him for a moment before we cross the ocean to the other one, because the details of what he had actually built matter enormously. His setup was not elegant. A steel container lined on the inside with carbon acting as one electrode. Carbon rods suspended from above, dipping into the liquid inside, acting as the other. The liquid itself was the key. That pale blue-grey mineral melted down to a temperature his equipment could sustain, with aluminum oxide dissolved into it. When the current ran, the liquid conducted it. The aluminum ions, stripped from their oxygen bonds by the electrical force, drifted toward the carbon lining and collected there as pure metal. The oxygen that was left behind reacted with the carbon rods and burned off as gas, which meant the rods slowly consumed themselves and had to be replaced. The whole thing smelled of heat and mineral, and something faintly sharp, like the air before a storm. It was crude. It was functional. It was the first working version of a process that would eventually produce tens of millions of tons of metal every single year. Now cross the ocean. Different city, different climate, different life entirely. A young man in his early 20s, working in a rented space in a building that also housed a printing shop on the ground floor, so the whole place smelled perpetually of ink and machine oil. He had reached the same theoretical conclusion independently through his own reading, his own experimentation, his own reasoning. The same mineral. The same electrical approach. The same basic apparatus arrived at through completely separate thinking. When he ran his process and got his first clean yield of aluminium, he sat with it for a moment, and then did something that tells you a lot about his personality. He documented everything first, every measurement, every observation, every step in the sequence written down in careful detail before he told anyone. He wanted the record to be unambiguous. Both of them filed for patents within months of each other. The overlap was immediate and obvious, and the dispute over who got there first became a formal, legal and scientific argument that dragged on for years. The man who had documented everything so carefully had his paperwork in order. The other had his professor as a witness. The argument about priority never fully resolved to everyone's satisfaction, which is why today the process carries both their names. Not one, both. A shared credit for a shared discovery that neither of them planned to share. What I find genuinely moving about this, when I think about it clearly, is what it says about the nature of the problem itself. Two people in different places, working with different resources, shaped by different educations and different life experiences, arrived at identical solutions. That doesn't happen by accident. It happens when a problem has become solvable, when enough surrounding knowledge has accumulated that the answer is almost visible to anyone who looks in the right direction with the right preparation. The solution wasn't waiting inside either of those two men specifically. It was waiting in the state of the science itself. And they were simply the two people who happened to look at the right time. Within months of both discoveries being confirmed, investors appeared. They always do when something real is on the table. A small production company was formed around the process. First in a modest facility near a river where water could cool the equipment, then expanding rapidly as the results proved consistent and the demand became clear. The smell of that first facility was apparently extraordinary. Hot metal and burning carbon, and the faint mineral tang of the melted flux, mixed with the coal smoke from the generators providing the electrical current. Workers wore heavy aprons and kept their distance from the vats when the current was running. The liquid inside glowed faintly orange at the surface. Aluminium collected at the bottom, denser than the melt, pooling in the carbon lining like a silver shadow, drawn off periodically and poured into molds. The price began to move almost immediately, not drift, move. Within the first year of serious production, the cost per unit weight had dropped sharply enough that people in the metals trade noticed. Within 2 years, it had dropped enough that the people who had invested in aluminum as a store of value started to feel genuinely uneasy. Within 5 years, the collapse was so dramatic and so complete that the metal that had sat under a glass case in a jeweler's window was now being discussed as a potential material for everyday industrial use. The aristocrats who had collected aluminum decorative objects found themselves in the strange position of owning things that were still physically identical to what they had purchased, still the same metal, still the same objects, but worth a fraction of what they had paid. The chemistry hadn't changed. The material hadn't changed. The only thing that had changed was the knowledge of how to make it. And that single change in knowledge had erased decades of accumulated scarcity in a handful of years. But here's the thing about cheap aluminum that most people don't think about. Cheap isn't the same as easy to make. The process worked, but it was hungry in a way that nobody had fully anticipated. To make 1 ton of aluminium, you need enough electricity to power an average home for roughly 20 years. Let that number sit for a second. Not a day, not a month. 20 years of household electricity consumed in the process of making a single ton of metal. This is the hidden cost that nobody talks about when they hold a soda can. This is the reason that, despite the process being discovered by 2 young men with modest equipment in modest workshops, scaling it up into something industrial required not just investment and engineering, but a completely different relationship with energy itself. We ended the last part with the price collapsing and investors arriving. But the investors who understood what they were actually buying weren't just buying a chemical process. They were buying a bet on electricity. Because without massive, cheap, continuous electrical power, the process was interesting, but not transformative. The metal would get cheaper, but not cheap enough to change the world. The real unlock wasn't the electrolysis method itself. It was finding places where electricity was so abundant and so inexpensive that the energy cost of making aluminium became almost negligible. Those places existed. They were found wherever fast-moving water could be captured behind a dam and converted into electrical current on an enormous scale. River valleys with steep gradients. Mountain regions where snowmelt rushed downhill through narrow gorges. Coastlines where tidal forces could be harnessed. The aluminium industry didn't grow where the ore was, it grew where the power was. And that geographic logic, power over ore, shaped the entire industrial map of aluminium production for the next century. The first large-scale facilities were built near rivers. The sound inside them was overwhelming. Dozens of electrolytic vats running simultaneously, each one drawing tens of thousands of amperes of current, produced a deep electrical hum that you felt in your chest before you heard it with your ears. The air was hot and sharp and carried the faint, bitter smell of oxidizing carbon from the anodes slowly burning away. Workers moved between the vats in heavy protective gear, periodically tapping off liquid aluminium from the base of each cell, the metal flowing out like dull silver water into waiting molds. It cooled quickly in the open air, the surface dulling from bright liquid to pale solid in seconds. The output grew steadily, then rapidly, then at a rate that made the early investors look like they had understood something profound about the future, which they had. The price per unit kept falling. Manufacturing industries that had been watching from a distance began placing orders. And then one specific industry discovered aluminium and immediately understood that everything was about to change. The people who were trying to build flying machines had a problem that was fundamentally a weight problem. Every component of a powered aircraft had to justify its mass. The engine especially. An engine heavy enough to power flight, but too heavy to be lifted by the wings it was supposed to drive, was useless. Every engineer working on the problem knew this. And every engineer working on the problem had been constrained by the materials available, which meant steel and cast iron and copper, all of them dense, all of them adding weight that had to be overcome before a single meter of altitude could be gained. When aluminium alloys became available at industrial scale, a mechanic working in a small workshop attached to a bicycle repair business was handed a specification for a flight engine and told to make it as light as physically possible. He machined the engine block from an aluminium alloy. The result weighed roughly half of what an equivalent steel engine would have weighed. The aircraft it was installed in flew 4 times on the same morning. The longest flight lasted under a minute. But it flew. And the reason it flew, one of the central physical reasons, was that aluminium had made the engine light enough to make flight possible. That first flight happened in the same decade that the price collapse had made aluminium industrially accessible. The timing was not a coincidence. It was a direct causal chain. 2 young men crack the extraction problem, the price falls, the material becomes available, an engineer uses it to solve a weight problem that had blocked aviation for decades, and suddenly humans are airborne. A chain of events that started in a dirt floor workshop ended in the sky. But what happened next with aviation, and with aluminium specifically, dwarfs that first morning of flights entirely. Because within a generation, the same logic that made a small propeller aircraft possible was applied to machines of a completely different scale. Enormous, rigid airships, the largest flying objects ever constructed by human hands, required a structural skeleton that was both strong enough to hold their shape under flight loads and light enough not to drag them out of the sky. Aluminum alloy was the only material that could do both. The frames of the largest airships ever built, structures spanning the length of several city blocks, were assembled from hundreds of precision-machined aluminum alloy components. Without the metal, those machines could not exist. Full stop. And then the wars came, and the scale of what aluminum meant to a nation that wanted to fight in the air became terrifyingly clear. The logic was brutal and simple. Aircraft require aluminum. More aluminum means more aircraft. More aircraft means control of the sky. Control of the sky, by the time large-scale industrial warfare arrived, was not a tactical advantage. It was close to a deciding factor. Governments understood this with a clarity that cut through everything else. Production figures for aluminium became classified information. The gap between what one side could produce and what another could produce translated directly into the number of engines and airframes and fuel tanks that would be in the air over the battlefield. Every ton of aluminium was a potential aircraft. Every potential aircraft was a potential shift in the balance of the conflict. One major industrial power was producing over 4 times the aluminium of its principal opponent at the height of the conflict. 4 times. That ratio showed up in the sky in the form of air superiority that gradually, then decisively, tilted the outcome of the entire war. Supply chains were built and defended specifically to keep aluminium moving. Agreements between Allied nations included aluminium shipments as a core strategic provision, not a secondary consideration. Factories ran continuously. Workers did shifts around the clock. The vats never went cold. The metal that a head of state had once used to impress dinner guests was now being measured in hundreds of thousands of tons per year, and those tons were the arithmetic of survival. And when the conflict finally ended, all of that production capacity, all of those factories, all of those workers didn't just stop. They looked for the next thing to make, and they found it in the most ordinary places imaginable. Stealing aluminium became a professional criminal enterprise, not petty theft. Organized, systematic, coordinated stripping of aluminium from infrastructure across entire regions, electrical wiring pulled from buildings in the night, structural components cut from bridges and sold by the ton, roofing panels lifted off industrial buildings while the owners slept. In some areas, the problem became severe enough that it disrupted power grids, delayed trains, and left buildings structurally compromised. And the reason it happened, the economic engine driving all of it, was a single remarkable fact about aluminium that most people have never thought about. Recycling aluminium requires only about 5% of the energy needed to make it from raw ore. 5%. Which means that a pile of aluminium scrap is not just worth its weight in metal, it is worth its weight in metal plus the enormous energy cost that does not need to be spent extracting it from scratch. For anyone with access to the right buyers, aluminium scrap was essentially free money. The factories that had been running at full wartime capacity needed raw material. They would buy scrap. No questions asked about where it came from. And that created a market that made certain kinds of people very attentive to where aluminium was sitting unguarded. This is the strange afterlife of a material that spent decades as the most prestigious substance in the world. It went from guarded like a crown jewel, to mass-produced for warfare, to so ubiquitous that people started stealing it off bridges. That arc, from palace dining room to criminal commodity in under a century, is one of the more disorienting things about this whole story. But let me back up slightly, because the transition from wartime production to peacetime everyday life didn't happen overnight, and it didn't happen in an obvious straight line. The factories existed, the process was proven, the workers knew how to run it. But post-war economies needed to find civilian applications that could absorb the kind of production volumes that wartime demand had required. Some of that found its way into construction, aluminium window frames and cladding panels and structural elements in new buildings going up across cities that needed rebuilding. Some of it went into transportation, lighter vehicle components, railway fittings, ship parts. And some of it ended up in the kitchen. The humble aluminium cooking pot became one of the defining domestic objects of the post-war decades. Lightweight, easy to clean, resistant to rust, cheap enough to replace when it wore out. For households that had spent years making do with limited everything, an inexpensive, functional cooking pot was not a trivial thing. It was a small daily improvement in the quality of ordinary life. Millions of them were produced and sold. The same metal that had been cast into ingots for emperors and machined into aircraft frames was now sitting on a gas burner with soup in it. Then came the can. The aluminium beverage can is so ordinary now that it is genuinely difficult to see it as the engineering achievement it actually is. A cylinder of metal, walls thinner than a human fingernail, strong enough to hold pressurized liquid without deforming, light enough to be carried by the dozen without effort, and manufactured at a rate of hundreds of billions per year globally. The tooling required to produce a modern aluminium can to the tolerances it requires is extraordinarily precise. The metal is rolled to a specific thickness, drawn and ironed into shape, trimmed, coated internally to prevent any reaction with the contents, printed on the outside, filled, sealed, and distributed, all at a speed and scale that is almost impossible to picture. And at the end of that entire chain, a person picks it up, drinks whatever is inside, and either drops it in a recycling bin or doesn't. If they do, those atoms rejoin the cycle. Back to the smelter, back to the rolling mill, back to the production line. A can recycled today can be back on a shelf as a new can within a matter of weeks. The energy cost is a fraction of starting from ore. The material loses essentially none of its properties. It can do this indefinitely. Aluminium is, in a very real physical sense, a permanent material. It doesn't wear out from recycling. It just keeps going. About 3/4 of all aluminium ever produced by humanity is still in use today in some form. That number is staggering when you sit with it. All the wartime aircraft frames, all the post-war cookware, all the building panels and car hoods and window frames and billions of cans, the vast majority of it is still somewhere in the system, still functioning as aluminium, still carrying the same atoms that were locked in clay for billions of years and freed by 2 men in 2 workshops. The world is, in a meaningful sense, built from aluminium that has already been used for something else. But here is the thing about this material that the recycling story and the everyday object story both slightly obscure. Aluminum is not just mundane. Underneath the surface of its ordinariness, there is chemistry that is so strange and so unexpected that it makes the history of the metal look almost straightforward by comparison. Because this same element, the one in the can and the window frame and the cooking pot, has other identities. Identities so different from a crumpled beverage container that most people would never guess they share an atomic foundation. And one of those identities involves something that sits in a jeweler's case under glass, illuminated by a small spotlight, priced at thousands per carat. The connection is real. It is not metaphorical. And it is one of the stranger things that chemistry has ever produced. The country sitting on top of 1/3 of the world's entire aluminum ore supply is also one of the poorest countries on Earth. Not slightly poor, deeply, persistently, structurally poor, in a way that has not meaningfully changed despite decades of extraction happening right there in the soil. The ore leaves on ships. The wealth does not come back in any proportion that reaches ordinary people. And the cruel, mechanical reason for this, the part that makes it not just unfair but almost architecturally unfair, is that the ore and the process that turns it into metal are permanently separated by geography. We established earlier that making aluminium requires electricity on a scale that is difficult to fully imagine. A single large smelting facility consumes as much power as a city with over 1 million residents. That kind of electricity only exists where someone has already built the infrastructure to generate it. Massive hydroelectric dams on fast rivers, geothermal plants tapping volcanic heat, industrial power grids built over generations with enormous capital investment. Those things exist in certain wealthy regions of the world. They do not exist in the places where most of the ore is. So the supply chain for your soda can looks something like this. The rock is dug out of the ground in a tropical country where the local population sees relatively little of the financial return. It is loaded onto a ship and transported thousands of miles to a port near a smelter. The smelter sits next to a dam on a fast, cold river in a northern country, or near a geothermal field on a volcanic island, or beside a massive hydroelectric installation in a remote region of a large country. There, the ore is processed first into powder and then into metal, using electricity so cheap that the energy cost becomes manageable. The metal is then shipped again to rolling mills and factories in industrial regions, where it is turned into sheet and rod and tube, and eventually into the products that end up in homes and offices and vehicles worldwide. Every continent touched it. Dozens of companies profited from it at various stages. And the place where the whole chain begins, where the actual rock came from, received the smallest share of that value by a margin that is not close. This is not a hidden scandal. It is documented and discussed by economists and development researchers. But it sits quietly underneath the ordinary fact of a beverage can in a way that most people never think about. There is something almost physically uncomfortable about holding that can once you know this. Not because the can itself is wrong, but because the distance between where it started and where it ended up, and who benefited at each step of the journey, is so enormous and so invisible in daily life. The can is light. The history behind it is not. And yet even this uncomfortable geography contains one more layer that most accounts of aluminum leave out entirely.
The ore itself, the bauxite that starts this whole chain, is not just sitting in neat deposits waiting to be scooped up. It was formed over millions of years through a specific geological process that only happens in certain tropical and subtropical regions, where heavy rainfall over ancient aluminum-bearing rock slowly leaches away everything except the aluminum compounds, concentrating them near the surface. The red and orange laterite soils that characterize these regions are essentially the planet's own version of a long, slow refinement. Nature spent millions of years doing the first step of the work. The rest of the chain is what humans built on top of that. Which brings us, in a strange way, back to the chemistry. Because while the ore is being dug from tropical hillsides and shipped to northern smelters and turned into metal and rolled into sheets and stamped into cans, the aluminium oxide that is the foundation of all of it is simultaneously one of the hardest substances on Earth, the basis of two of the most valuable gemstones ever traded, the active medium of the first laser ever built, and an ingredient in a reaction so violent it melts steel with no external heat source required. All of that is the same compound. All of it is aluminium oxide, the thing that was too stable to break open for most of human history, the thing that locked the metal away so effectively that 100 years of brilliant chemistry failed to crack it. The oxide that coats every aluminium surface and protects it from corrosion is chemically identical to the mineral that, in its pure crystalline form, sits just below diamond on the hardness scale. Add a trace of one specific element to that crystal, and it turns deep red. That is a ruby. Change the trace element, and it turns vivid blue. That is a sapphire. Both of those gemstones, the ones in engagement rings and royal crowns and museum collections, are aluminum oxide with a small amount of impurity, the same chemical foundation as the coating on a crumpled can. The difference between a stone worth thousands per carat and a piece of packaging worth fractions of a cent is a trace element and a crystal structure. A researcher working in a laboratory in the early 20th century grew synthetic versions of these crystals deliberately, controlling the impurities to produce specific colors, and sold them as industrial abrasives and eventually as gemstone substitutes. The process he developed is still in use, but his synthetic crystals found one application that he almost certainly did not anticipate. Another researcher, working decades later, took a rod of synthetic aluminium oxide crystal doped with a specific element and used it as the core of a completely new kind of device. He fired a burst of light into it and got a concentrated, coherent beam of light out. A laser. The first one ever built. It worked because of the specific way that aluminium oxide crystal absorbs and releases energy at the atomic level. The first laser in human history was, at its heart, an aluminium device. And then there is the reaction that goes in the opposite direction entirely.
Take aluminium in powder form, fine enough to be almost dusty to the touch, and mix it with iron rust, which is just iron oxide, iron that has already grabbed its oxygen. Pack that mixture tightly and apply a source of ignition. What happens next is not an explosion in the conventional sense. It is a thermite reaction, and it produces heat so extreme that iron melts in seconds without any external furnace. The aluminium tears the oxygen away from the iron with such force and such speed that the temperature in the reaction zone reaches levels that would liquefy most metals. The iron that is freed in the process pools as a liquid. The aluminium oxide that forms is a white slag. The whole thing is over in moments. This reaction cannot be stopped with water. Water does nothing. The reaction contains its own oxygen source and does not need the air. The only thing that can interrupt it is to smother it completely, and even that is difficult once it has started. Railway maintenance crews use a controlled version of this reaction to weld track joints in the field, pouring the liquid iron directly into the gap between rail ends, creating a seamless bond without any external power source. The same chemistry that makes aluminium a passive, stable, corrosion-resistant, everyday material is also capable of producing one of the most intense and unstoppable thermal reactions in industrial use. The same element, the same oxide. Completely opposite behaviors depending on the form and the context. This is the thing about aluminium that I keep coming back to. The thing that ties the whole story together in a way that feels almost designed. Though of course it is not designed at all. It is just chemistry, just physics, just the behavior of a specific arrangement of protons and electrons that has been present in the universe since before our planet existed. The story of aluminum is not really about a metal. It is about the gap between what exists and what we understand. For billions of years, this element was everywhere. In the rock, in the clay, in the compounds that ancient craftspeople used daily. Nothing about its presence was secret. The universe was not hiding it. The only thing standing between humanity and this material was knowledge, specifically the knowledge of how to ask the right question. Not where is it, but how do we get to it? Not what does this compound do, but what is inside it. Not how do we break this bond, but what if we stop trying to break it chemically and try something completely different instead? Every door in this story was opened by someone who changed the question. The chemists who moved from using aluminium compounds to asking what was inside them. The researchers who shifted from furnace-based extraction to electrical extraction. The two young men who stopped asking how to attack aluminium oxide directly and started asking what they could dissolve it in instead. The engineer who asked not what is the strongest material, but what is the lightest material that is strong enough. The barrier was never the material. It was always the framing of the problem. And here is what makes that genuinely unsettling in the best possible way. If the most abundant metal on Earth spent the entire span of human civilization locked away not in a remote location, but in the ordinary clay under everyone's feet, waiting for nothing more than the right question, then what else is sitting in plain sight right now? What material, what energy source, what solution to a problem that currently seems permanent is already present and accessible and simply waiting for someone to stop asking the old question and try a new one? That is not a rhetorical question. That is the actual situation we are in. So here is what I want to ask you directly, and I genuinely want your answer in the comments. If aluminium, the most common metal on Earth, was invisible to humanity for our entire history until someone changed the question. What do you think we are missing right now? What is the clay under our feet today that we are all walking past without seeing? Write it below. I want to read what you think. If this story gave you something to think about, hit the like button and subscribe. There are more stories like this one, and every like genuinely helps more people find them.